So, welcome back. In the previous class, we introduced the notion of a semi group T and its generator A. We obtained some simple properties of T as well as this generator A. So, in particular, so let me again repeat that. So, A is a densely defined closed operator. Okay. So, we already also saw given a semi group, we already have a solution of the abstract Cauchy problem. So, before we proceed further, it is always better to have some concrete examples. Okay, so this. So, in the examples I will not do all the details. So, I define the semi group. So, you have to verify that it is indeed a semi group. So, you have to verify the two properties in the definition and find its generator. Okay. So, the first one is just little L2. Okay. So, x in L2 I denote it by. So, it is a sequence x1, x2, etc. So, squares you can even take LP. So, there is no problem. Okay. So, define T of T, this is from L2 to L2. So, we have to define by T of T x, again this is going to be a sequence. So, I have to tell what is its nth coordinate. So, this is by definition T n square e to the minus T n square x n. So, n equal to 1, 2, etc. Okay. So, verify that T t is indeed a semi group. Is a semi group and find its generator. Okay. So, you also see is this a group. Okay. So, that also you, so whenever a semi group is given, you should also verify whether it is in a semi group or a group. Is this a group? Okay. So, that okay. So, this is a simple one. Okay. The next one is the function space. So, here x is either UCB, I will define what this is, R plus is 0 infinity, the positive real axis, or the LP okay. So, this one let me define this. So, this is set of all F from R plus, that is 0 infinity, either R or C, F uniformly continuous, that is UC, and bounded. and this is equipped with sup norm. Okay. So, you can verify that is a Banach space. Okay. X is this UCB is also Banach space, and these are usual the Lebesgue class. Okay. And on this space X, so now we are going to define semi group of left translations. Okay. So, TT. So, T of F is in X. So, again that is a function. So, I just define this is F of X plus T. So, this is for X bigger than or equal to 0 and T is also bigger than or equal to 0. Okay. So, we can also consider instead of R plus the entire real line, and in that case this T T is defined for all T in R. So, we get group of translations both left and right. Okay. So, as you take T positive or T negative. Okay. So, let me just concentrate on this thing. Okay. So, verify this T T is a semi group. So, let me just mention here that for if X equal to UCB, the strong continuity follows from uniform continuity, because in this space the elements are uniformly continuous. Okay. So, if X is LP R plus, the strong continuity follows from the continuity in the norm. So, you see so you are going to use all the tools developed in analysis in the first part of this course. Okay. But work out the details. Okay. Write down the definition of the strong continuity and see that the properties of the functions in this respective spaces are used very much. Okay. And as far as the generator is concerned, okay, so let briefly, and this is how you guess the form of the generator in general and then try to prove it rigorously. Okay. So, if F belongs to X, either UCB or LP. So, for the generator we want this limit, now they are functions. So, I have to as T this limit as T tends to 0 should exist, then that particular F belongs to the generator. Okay. But now, so this should converge in the respective norm of this X. So, either in the sup norm or in the LP norm. Okay. So, but that already gives us a clue that for f to be in dA, this f prime, okay, let me just write here, should exist and f prime should belong to again x, then only you can define that. Okay. For uniformly continuous functions, so we can expect this to be classical derivative, and that again should be uniformly continuous and bounded. But for LP functions, so we should consider this only in the fictions, right. So, expect okay. So, this for x in UCB R plus this dA is going to be set of all f in x, okay, and f is okay, differentiable and f prime is also. Okay, so this for x in LP. So again this dA f in x, but now this f prime exists only exists in the fictions, and of course f prime should belong to x. Okay. So, for the both spaces we can write this in a unified way. So, define D. So, either x is UCB R plus or LP R plus. So, f is in x, f is AC log, I will again define what this is, and f prime in x. Okay, so this is the space of locally absolutely continuous functions. So, that means this f is absolutely continuous on every finite interval of R plus, and then by theorem of Lebesgue it follows that f prime exists almost everywhere, and we require that f prime is also in x, either UCB or in LP. So, let me make a comment here. So, we have defined the Sobolev spaces, just side remark. Okay. For so here I am taking this. So, we have defined this W1P omega in general, but so we have this is f in LP in R plus such that the weak derivative or in the sense of distributions, weak derivative f prime is also in LP. For the special case of the real line, okay, so this will not work in higher dimensions. This is same as f is in LP or plus f is locally absolutely continuous and f prime belongs to again LP R plus. Okay, so verify this. Okay, so this you might not have done it. So this this space D we have defined for at least the class of LP, it coincides with W1P. Okay, and now you verify that. So verify. So the generator A for the left translation semi group, okay, is defined by this dA is equal to D. Okay, so this is the D. Okay, and A is defined by F equal to F prime. Okay, so this is so we have that semi group of left translations and its generator is given by the derivative. So one more example. So let me this. So this is bit hard. So this is Poisson kernel. So in a way it is a cousin of the heat kernel. Okay, so again this is in R. Okay, so we are so P for Poisson. So you consider this. Let me just write it. 1 by pi T by T square plus x square. So T is positive and x is in R. So it's a nice function, but it is not in the Schwarz class. So in fact, let me just write that. So PT. So since we are working in L2 here, so its Fourier transform that you need is given by, let me just e to the minus t mod chi. Okay, so t again t positive. Okay, just verify that. So what is the semi group? So define Tt from L2 R into L2. So for the this is a hard problem, okay, but very interesting one, and you learn lots of analysis. So you can make full use of Fourier transform techniques by Tt. So I take an F here. So this is convolution of Pt with F. So let me write that at least once. 1 by pi or t by, so t also we can take out. So, this is integral over r f of y divided by t square plus x minus y square dy. Okay, so this is for t positive. Okay, and you define this t0 of f equal to f. Okay, so this f is in L2. Even this semi group property is not immediately clear, but I just we can use, since it is a convolution, so we can use the Fourier transform to see that the semi group property, when that is not immediate, right, semi group property follows by taking Fourier transform. Okay, so this t of t1, t of t2 f. Okay, so this is t of t1, this is pt2 star f, and then we have this pt1 star pt2 star f, and you use associativity and now you use the Fourier transform of Pt I stated. So, just to conclude that this is by taking Fourier transform. So, if you take Fourier transform, it will be product of the Fourier transforms, and again you take the inverse portion. So, you do get this, and that is just T of T1 plus T2 f. So, again for the strong continuity, you use strong continuity follows. Of course, you have to work out. I simply say it follows from the continuity in the norm. Okay. Now, a brief discussion in the remaining time, a brief discussion about the generator. Okay. Generator. So, what we have to look for, this TTF minus F by T. So, you have to consider limit t tends to 0. So, that is a convolution. Of course, you can do like that, but we can use the Fourier transform. This is for just guessing, and then you have to really prove it rigorously. Okay. So, taking Fourier transform, so T, so this is just T inverse TTF hat minus F hat. So, that gives us T inverse. So, this is PT star F. So, when I take the Fourier transform, it will be product of PT hat and F hat. So, let me write that PT hat F hat minus F hat. So, this is T inverse e to the minus t mod j, this is minus 1 f hat. Okay. So, p t hat is e to the minus t, and for just formally this, what is the, as t goes to 0, what happens to this? This goes to, so this is, if you write as 1 minus t mod j, so you get minus mod j f hat. Okay. So, expect, so let me again write j. So, dA, so now everything in terms of the Fourier transform. Okay. So, this f in L to Rn, L to R, not Rn, that either minus or plus is that. Okay. Just mod f hat is also in L2. Right. And the form of AF again in terms of Fourier transform, we just get is minus mod j f hat j. And what is this operator? What is this operator? So, let me just, of course, you have to make all the arguments rigorous here, but at least we can guess the form of the generator. Okay. That is the first important step, and then you try to prove that all the computations are valid. Okay. So, this, let me just mention, that is an important operator. So, Hilbert transform. So, you see lots of analysis coming to play. So, this I am not going to again define it in. So, it is in fact it is a singular integral operator. So, again let me define in terms of defined in using Fourier transform. Okay. So, you can dig the literature if you are interested in very nice properties of Hilbert transform, that is in one dimension. Higher dimensions, this theory is developed by Ries, and they are called Ries transformations. Okay. So, this is HF, H for Hilbert. So, again defined by, so let me write that HF j minus I sin of j f hat j. So, if you define this H without the Fourier transform, it is, I will just write that, convolution with this singular function which we have studied in detail in the first part of this course. So, this is, so you have to take convolution with this function. Okay. And then when you transform using Fourier transform, you get that. Okay. So, this generator is expressed in terms of the Hilbert transform generator. So, let me just write that. So, AF is equal to, so let me just write what is that, minus H So you can, so if you write this abstract Cauchy problem with this generator A, so du by dt is equal to AU, and now you see this AU prime. So it is in some sense second order, but in a singular way. So it's not as nice as the Laplacian. So the semi-group theory can also handle singular equations. So that's an important observation through this example. So if you are interested, you can look into the literature regarding this Hilbert transform and other properties. Okay. So work out all these 4 examples in order to get familiarized with these new concepts, semi group and its generator. And in the next class we will continue this discussion and with some more properties of the generator, and then we will go to Hilbert theorem. Thank you.